자, 우리 시작하겠습니다. Alright, thank you very much for showing up. So today we have makeup class. So we're going to continue the covering the concept of locality. So let's think about the big picture again. So here, the idea is we actually have two different types of memory, like SRAM and DRAM. And SRAM is generally small and expensive, but actually it's really fast. In contrast, DRAM is relatively large, cheap, but actually is slow. So the question is how we can make an ideal memory system that is as fast as SRAM, but as cheap and large as DRAM. That's the goal of the architecting this memory system. So to make this like ideal memory system, we exploit the property called locality. So here is a example of exploiting locality. First of all, is book storage. We actually have multiple places we can place books, and level 1 is like a desktop. You can actually put your books on your desk. It's really fast to access, but it's a relatively small. It actually has very small capacity. But level 2 is bookshelf, which is it's a little bit slower, but it's much larger, right? So there's trade-off between the two. And level 3 is maybe the Kwanjong library, which actually has huge capacity, but it's actually really slow to access, right? Likewise, the second example is like a hierarchy of like putting like a cookers in a kitchen. So I would say even my grandma understand the concept of hierarchy because she always put those she used most frequently on a hanger, which is easy to access. And the level 2 is drawer. You actually put some cookers that's you use it, but not as frequently as those actually put. But still you use quite a bit. And level 3, which is basement, or like some storage space. It's a very slow to access, but it has huge capacity, right? So it's basically idea of hierarchy. So if you apply the same idea of like a hierarchical organization of like a storage space, we can actually put this memory system, architect this memory system like this. So if you see this main board of computer, this is motherboard of modern like a desktop PC. Usually we actually place level 1, level 2, and often level 3 like memory system is on the same chip of the CPU. So we can replace some like a fast SRAM and on this like inside this CPU chip. So that's called a cache. Okay, so we actually have like a level 1 cache, level 2 cache, and level 3 cache. And the level 4 is main memory, like DRAM. So if you see, like a few slides ago, this one is the DIMM, like a DRAM, DIMM. So memory module. So you actually put these kind of things in this slot. Today's the mainstream memory device like a DDR4. So we actually double data rate synchronous DRAM like a DDR4 on this like a slot. So this is DDR4 slot. So you actually put those DIMM, and they actually serve as either level 3 or level 4 depending on how many levels you have on chip. On the CPU. So it's actually slower but much bigger than like on-chip SRAM. How about level 4 or 5 after like a DRAM? So we actually have storage like SSD or hard disk, which has like a terabyte like range capacity. And levels maybe 5. If we further go down, maybe we actually have cloud storage. So it actually has almost like unlimited like a storage, right? So let me discuss the principle of locality. So what is locality? In Korean, locality is called maybe it's easier to understand if in Korean. This is called 지역성. So it's a locality. So the principality of locality is as follows. The programs tend to use data and instructions with addresses near or equal to those they have used recently. That's the principles of locality. So that means, if you use like access like a certain like access instruction or data, it's very likely that you're going to access the same thing again. in the near future. That's locality. Also, okay, there are two flavors of locality. The first one is like a temporal locality, what I just explained. So once you actually access a certain piece of data or instruction, it's very likely that you're going to access the same piece of instruction or data again in the future. That is called temporal locality, in time, locality in time. Secondly, the second flavor is spatial locality. The spatial locality means if you access like a certain piece of data or instruction, it's very likely that you're going to access like those nearby and those like instructions or data nearby too. Okay, so if you see the figure, for example, if you access like this specific word in your program, then it's very likely that you access like this one as well. So this one is like called spatial locality in space, right? Because you access this one, then likely to access like those like items nearby as well. So this is called like a spatial locality. So we exploit this like a locality in the program to optimize this memory system. Okay. Then what can be like a reasonable strategy to in like organizing this memory hierarchy? If your program actually have locality, then what we can do to optimize the performance of your memory system? Let's say you have like an on-chip SRAM and off-chip DRAM, and your entire data is currently in the DRAM. Then which data you want to actually put in the small on-chip SRAM? Any guess? Yeah, he first completely right, completely correct. So if you access like a certain item, you probably want to put those like items nearby into on-chip SRAM too, because they are likely to be accessed in the near future, right? By that, we can actually exploit spatial locality. The second thing is we also want to put like those items that are accessed into the on-chip SRAM too, because it's likely once you actually access certain item, that item is likely to be accessed again in the near future. So once you have access to certain item, then you probably want to put this item into fast memory because it's likely to be accessed again, right? It's as simple as that. So that's pretty much it. I mean, that's the whole idea of caching. Okay. So whenever in summary, if you actually access like a certain item, first of all, you place this accessed item into the fast memory, and secondly, you also not only those items, but those items, those like a nearby, neighboring items also you put it into the fast memory. That's the idea. That's it. That's pretty much it of the idea of caching. Okay. Then if you actually place like those that's called a block. So you actually have an item, then those nearby, you actually have like a certain like a larger like unit of memory, piece of memory. That's called a block. So if you actually place the entire block of memory, then you actually have better chance to service like a later request from the fast memory, right? That's basically the whole idea. So let's think about this locality example. Which program actually has very high degree of locality, and which program actually has like a lower degree of locality. For example, if you actually, let's say you have your program actually have like a random access type. Let's say your program access some like a random memory location in your program, then would it actually have a lot of locality or not? Yes or no? No, right? Because you do like a random memory location, there's no locality, right? The locality means you either access the same item again and again, or you access the item nearby and neighboring items, right? So if you actually have like a truly like random access, memory pattern, that program doesn't have any locality, right? So let's think of this example. So here we have a very simple for loop, which actually computes a sum of array elements, right? Array A. So let's say we have array A, integer array, and this array actually has n elements. So we actually have a for loop. So keep like accumulating the value of A of I to the sum, right? So, and we finally return the sum value. So let's think about what kind of locality is there. First of all, so we actually have like this item. So because you execute like this program, by accessing A of I, you have to execute a load instruction, right? Load the value of if you you actually unfold it, it'll be like something like this. Sum is sum plus a of 0, followed by sum plus equal a of 1, sum a of 2, blah blah blah, up to a of n minus 1, right? So let's think about this one. You keep accessing like this thingy, starting from a of 0, next thing a of 1, a of 2. So if you access like this array a of I, what kind of locality is there in this access pattern? Temporal locality or spatial locality? Spatial locality, right? Because you access a of 0 followed by a of 1, which is adjacent, and a of 2, which is neighbor again. So this one is a spatial locality, right? Then what about the sum variable? Let's say sum is in your memory. Sum is a memory variable. Sum is actually in memory. Then what kind of locality is there in accessing this sum? Yeah, actually you can use register. Yes, that's true. But yeah, still, I mean, even though, let's not worry about where this sum is actually placed. Either it could be either like a register or memory. Of course, if you have a lot of temporal locality, probably you want to promote it to like a register variable. But in this case, you just purely think about this as certain like an abstract variable. We don't know whether it's like a memory in register. So if you do that, just by seeing the access pattern, this one actually has very ample temporal locality, right? Because you read the old value of a sum and add new value, update it and then store it to the sum variable, update the sum variable again, and you read the value and then add like a new, the a of I plus 1 and so on, right? So this sum variable actually has, very ample temporal locality. What about instruction? So this one is about data. What about instruction? If you execute this program, the execution flow will look like this. You first, start from sum, and you go to 4. Sum, go 4, and you basically make a loop like this. You continue like these two lines, like a 4, sum, 4, sum. You keep, repeating like executing like this thing, right? And finally, once you're done with the loop, you exit the loop, and you're done, right? Like this. The program like control flow will look like this, right? So, you basically make a reference instruction in sequence, right? Because you start from first line and second like a 4, and go to sum. You actually execute like a program in sequence. Then, what kind of locality is that? It's spatial locality, right? Because you start from the first line and move on to second line and go to third line. Of course, each line actually gets translated to multiple like instructions, right? So you continue executing like instruction one by one, but you also, this one is like a spatial locality, but you actually have a loop. So that means you execute the same set of instruction again and again and again and again, right? So that's actually temporal locality. So in summary, in this program, both data and instructions actually have ample locality, both a spatial locality and temporal locality. Okay? So let's think about another program, another example. So here, if you are really like a good programmer, I mean, let's say, if you are like a ninja, like excellent, like good programmer, then you should be able to look at a code and get some like qualitative sense of what the performance will look like. Okay. So the question is, let's think about this simple program. So this one actually has it's just like two-dimensional array version of the same thing. So we keep accumulating the value of an element in array A, and now this one is the only difference is two-dimensional instead of one-dimensional. We actually have two-dimensional array. So this one actually has loop outer loop I and inner loop j, and it actually keep accumulating the value of a of I and j. Then does this function actually have good locality with respect to array A? Yes, right? Because if you see the memory layout, So if you have a two-dimensional memory, let's say this is a memory layout. We actually have, A of 0 and 0 here, followed by which one? What is the next item in memory space? 0, 1, right? So, and A of 0, 2, and so on, right? And then finally, if you're done with like n minus 1, now the next one is A of 1, 0, right? And in this program, the sequence of access is A of 0, 0, 0, 1, 0, 2, because J is an inner loop, right? So you have 0, 1, 0, 2. So the access, it will be like we access this one, followed by this one, followed by this one, followed by this one, and so on, right? So this one actually has a very nice, like a stride one access pattern, which shows ample spatial locality, right? But what about this one? So this is the same loop, but now we actually interchange the order of J and I. Now the J becomes outer loop, and I becomes inner loop, right? What the access sequence will look like, we first access A of course, 0, 0. And then the next one will be A of 1, 0. Next one will be A of 2, 0. And so on, right? So in this case, the access pattern will look, if you have, we actually have the same memory layout for array A, then this one will look like, the first access will this one, first two access will goes to this like element, and second one will be like this, and third one will be like this, fourth one will be like this, right? So this one actually has very poor spatial locality because it actually jumps a lot. I mean, the next axis actually has far away from the current one. So this one actually has good locality, and this one actually has very poor locality. So which one will perform better, you think? This one or the previous version? The previous one will definitely perform better. It's like it's many times, like some number of times. I mean, more than 2x difference. So this one actually performs worse. By the way, this technique. By the way, in this example, we don't even though you change the order of the loop, the outcome will be the same, right? Because this like addition is associative and commutative, right? So it doesn't really matter which order you actually sum this up, right? If you have like a two-dimensional matrix like this, you can either sum this element in this order or this order. It doesn't really matter as long as you add them up, right? So because the reason is this integer addition is commutative and associative. So the order doesn't really matter. So this technique is called, by the way, this technique is called loop interchange. So loop interchange is kind of optimization, to increase the locality of access by changing the order of the loop. That is called loop interchange. And if you take this compiler course, probably the course will cover a lot more about this loop optimization. And this one is very well-known optimization technique of like loop unrolling, loop on interchange, peeling, all these things. So here there's another question. Can you apply loop interchange to make this program perform well? So in this case, now we have like a three-dimensional loop, a three-dimensional array, A of k, j, I, and now we actually have like a three-nested loop, I, j, k, right? So in order to make this program perform best, how you actually have to interchange the loop? What will be the order of the loop? So currently the order is I, j, k, right? So, but if you want to, maximize the locality of access of this loop, how you should interchange the loop? I하고 J loop을 바꿔? 이렇게? What is the order? You mean like a J, I, K? That's what you mean? Any other guess? Reversely. K, J, I, K, I, J? Right? Okay. Let's do a poll. So this was choice number 1. This is choice number 2. Which one will be better? So, question number, choice 1. You don't stand with your own, you don't stand with your own answer. Sorry for that. How about the choice number 2? Okay, this is consensus. This one actually performs better, right? Because if you, place those loops in this order, then now you know that at the axis pattern will be A of 0, 0, 0. The next one will be, the innermost loop will be J, right? So now we actually increment J by 1. So it will be 0, 0, 1, A of 0, 0, 2, and so on, right? So this one is the best. Oh, you mean the cache size? So I'm gonna, actually we're gonna get there, but maybe I can go give you a little bit of preview. Oh, it's not there. So typically this is your hierarchy. So level 1 cache is typically in the size of somewhere between 16 kilobyte to 16 kilobyte to 64 kilobyte. So that's kind of typical range for like an L1 cache. So L2 cache, if you have like L2 and L3, like today's like a desktop PC actually have L3 cache. So L2 cache is somewhere between like 512 kilobyte to like 1 megabyte range. It's per core. Actually 256 to 1 megabyte is like a per core cache. And the level 3 cache is generally like shared by all the cores in your CPU. So the size is somewhere between maybe like a 4 megabyte to like 24 megabyte. So it has some like a tenth of kilobytes. Level 2 is somewhere between like hundreds of kilobytes to like up to like one megabyte maybe. And this one is somewhere between like 4 to like maybe 24 or 20 something megabytes. So that's a typical size. No. So we don't really move the whole page into the cache. So the page is like a lot larger, like maybe like a 4 kilobyte page is typical. But single page can be broken down into multiple blocks. So typically the block size is about like a 64 kilobyte is a typical size. So even if you actually have, let's say you have page, like 4 kilobyte page, but only like those blocks in the page which you really access, those blocks will be actually placed in the cache, not the entire page. So entire page is actually reside in the main memory, but you only selectively cache those like blocks that are accessed into the cache. Right. So let's go back. 해줘요. So Smart Compiler actually does loop interchange. I mean the compiler does this optimization for you. 그러니까 컴파일러가 안 했다고 가정했을 때, 그냥 이 코드를 그냥 그대로 돌렸다고 가정했을 때, Smart Compiler actually does loop interchange for you. I mean, it's kind of compiler optimization, but we are assuming no such optimization is applied. I mean, just we assume this code run as it is, then the performance will vary a lot. I don't know. Perhaps like this maybe loop optimization may not be turned on by default. Maybe you actually have to give like a special flag in your compiler to turn it on. So it actually compiler dependent. But some compiler do. Some compiler actually do automatically interchange to optimize the performance of the loop. But it may not be turned on by default. But actually some like special flag you can turn it on. So. And in GCC, probably it's not turned on, I assume, yeah. Okay. So here is again, this is the concept of memory hierarchy, because most of this program actually have some locality in it. So access in terms of access pattern, they actually have locality. So by exploiting this locality in the access pattern, now we can put more more frequently used data into the place those data into the cache, and the other data is placed in like a slower like a DRAM, right? That's the basic idea. So there are some like a fundamental and enduring properties of hardware and software. So of course, the first point is fast storage technology costs more per byte, right? Like SRAM. For example, like this one, fast storage is example is like SRAM. SRAM it takes more area, so it's actually more expensive. So you should have less capacity and require more power because it takes like a lot more area than this like a small like a DRAM. The gap between CPU and memory speed is widening. Last time we actually saw this like a trend curve. On x-axis we have year, y-axis we actually had some like the performance like access time like of SRAM, DRAM, and CPU cycle time and so on, right? And then we saw that one of the trend was the gap between CPU cycle time and DRAM access time gets widened, right? So in 1980s, it only took like one CPU cycle to access DRAM, right? But in like in 2015, it takes like 100 of cycles to access like a single like a memory access in the DRAM, right? So there's a widening gap between the CPU and memory speed, and also on software front, well-written programs tend to exhibit good locality, right? Because if your program is well-written, well-optimized program, it actually has very good like locality in your program. So we by combining all these like properties together, we can design cache, right? So that to provide the illusion of very fast and cheap memory. So these fundamental properties complement each other beautifully, and they suggest an approach for organizing memory and storage system known as memory hierarchy. Okay. So let's move on to details of what's the memory how we can organize this memory hierarchy, especially in cache. So I've shown you this like a diagram before, but there's this one actually shows a hierarchy of memory. So if you it looks like a pyramid, and if you go up in the hierarchy, so this one is more like a smaller, faster, but more expensive, right? The fastest but most expensive is like L0, and if you go down the level, like from L0 to L2, L3, and so on, if you go down in the hierarchy, it's actually cheaper. Actually, you can offer more like a capacity, but it's much slower, right? So the level 1, the top of the hierarchy is a register. So in our example, we only have like 15 registers, right? So it's a very small piece of memory. Only like you can hold like 15 like quad words, right? 15 quad words. It's a very small piece of memory, but this is fastest, right? It only took like one cycle to access, right? So CPU register holds words retrieved from L1 cache. And the next level is level 1 cache, like SRAM. It's built using like SRAM. So L1 cache is next level. As I said, the typical capacity is like tens of kilobytes. That's kind of typical number. And the next one is like a level 2. So here is a trade-off. Even though you actually use the same technology, level 1, level 2, level 3, they actually use the same like SRAM technology. But generally speaking, if you actually have larger capacity, that tends to be slow, right? Let's say you build like SRAM array, like a 4 kilobyte array and maybe 4 megabyte array. Which one actually takes like more time to access? 4 kilobyte memory array and 4 megabyte array. Which one actually take longer to access? Yeah, larger one takes longer time, right? Because you actually, first of all, it takes actually longer time to find the specific cell you want to access, right? Because you have much more, greater like a cell, number of cells. So that if you want to actually locate a specific like a word in the cell, it takes longer to find that cell, right? That's the first thing. And then once you find it, you need to actually transfer this data through I/O, right? To the other block, right? But it takes like a longer time to transfer this data to the outside because array is bigger. So now you find here the wire is longer. You actually travel longer through like a longer wire to get out of the array, right? Because now array is much larger. So combine all these regions, even though you use the same technology, SRAM, or regardless of like SRAM, DRAM, or flash, regardless of the technology, if your memory gets larger, then its access time gets longer. Okay, so that's basically the relationship between L1 and L2 and L3 cache. So this one actually typically have like a tens of kilobytes, and level 2 holds cache lines retrieved from L3 cache. It's kind of basically this L1 cache actually holds a subset of what is held in L2 cache, and L3 cache actually holds like a subset of what is held in L3 cache. L3 cache holds data which is subset of main memory and so on, right? So there's like an inclusion like property. So like upper level data is actually a subset of like a lower level, the next level data. Okay, so that's the relationship. So L1, L2, L3, up to like this point, this one is on CPU chip. Okay, and this one is like a DRAM off chip. This is off chip DRAM. And this is disk. And this one is more like a cloud or some like a remote storage. Okay. So that's the hierarchy. That's like a hierarchy of memory. Then what is cache? So cache is a smaller, faster storage device that acts as a staging area for a subset of data in a larger, slower device. Okay, so it's kind of that's what it is. So it's kind of as I said, this cache actually holds like a small subset of the next level of storage, right? So so you can say something like, so L1 cache, level 1 cache is a cache of L2 cache, and level 2 is a cache for level 3 cache. And level 3 is a cache main memory. And main memory is cache for local disk. And local disk is a cache for the cloud, and so on, right? So that's basically, that's the general like a concept of cache. Smaller, fast storage device that acts as staging area for the subset of data in a larger and slower device. So fundamental idea of memory hierarchy, as I said, for each K, so for every K, a faster, smaller device at level K serves as a cache for the larger, slower device at area K plus 1. So here, this is a level 0, level 1, level 2, level 3, right? So the lower level, the upper level serves as cache for the lower level, the next lower level. So that's basically fundamental idea of memory hierarchy. So why does memory hierarchies actually work? Because of the locality, right? Because we actually have locality in your program. So program tends to access data at level K more often than they access the data in level K plus 1. Because once you access some data, that data is likely to be accessed again. And also like their neighboring data also is likely to be accessed again, accessed in the near future. So the idea is you actually put only those, like a small subset of data that were recently accessed, right, into the cache. Then that data is more likely to be accessed again, much greater with a much greater probability. So storage at level K plus 1 can be slower, thus much larger and cheaper per bit. So in this way, you can provide, basically take the best of both. The most frequently accessed data, most recently accessed data is placed on level K for fast access, but still you actually have, next level, which actually provide much greater capacity. So from like a programmer's view, it looks like, it's actually as fast as level K, but as like large as level K plus 1. Okay. So the memory hierarchy creates a large pool of storage that costs as much as the chip storage near the bottom, but that serves data to program at the rate of the fast storage near the top. Okay. That's the big idea. So here's general cache concept. Regardless of the level, this one's kind of general caching concept. So in memory, this one actually is larger, slower, and cheaper memory viewed as partitioned into blocks, right? You actually have large like a capacity, but now you actually you partition this like a space in like a fixed like a size. Okay, you have like a large space, and this one is like a fixed size. You mentioned like a page. Page is kind of such example. Page is kind of page is kind of a block. I mean, you divide the entire, the disk space into like a page size, and then the page is kind of, unit of transfer between disk and main memory. So, it's the same for, same for the processor cache. So let's say you can think of it, for example, let's say this is memory. Let's say this was, for example, it's like a DRAM. So now, let's say you have like 8 gigabyte DRAM in your system, in your like a PC. Then you divide it into, let's say this one is like a 64-byte block. Okay, so you actually have like 8 gigabyte like physical like a memory, like a DRAM space. But now you divide this like memory into 64-byte blocks. Then there will be a huge number of blocks, right? Because now you divide into like a fixed size block, and you can actually have this one is block ID. Right? Because now we have a huge number of blocks, and each block actually has some ID, right? And then you have a number of blocks, and so this one is like a partitioned into block, like a main memory, and cache is smaller and faster and more expensive memory caches. A subset, which actually hold a subset of the blocks. Okay. So and we actually pick the data. So then the question is, which subset we want to place in the cache, right? Because we actually have a lot more like blocks in the memory than actually we can put it in the cache. So we actually have to select which block to place in the cache and which block to not. So that's the decision we have to make. And data is copied in block size transfer units. So block is the unit of copying from lower level of a hierarchy to upper level of a hierarchy. So even though you access like a specific like a word, you copy not only just that word, but also the entire like a block. In this case like a 64-byte, entire like 64-byte like a block, which actually contains that word being accessed, will be transferred into the cache. 예시로 64바이트로 한 거예요. 근데 64바이트가 티피컬한 값이기도 해요. 사실 우리가 쓰는 그 인텔 CPU 같은 게 64바이트가 맞고요. 그리고 옛날에 다른 CPU 같은 건 128바이트나 뭐 256바이트로 하는 경우도 있었어요. 근데 일단 64바이트가 제일 그냥 널리 쓰이는 값이긴 해요. This is an example, for example. Not necessarily 64 bytes, but it's kind of example. So let's say you access a certain like a memory address that actually falls in block 4. Let's say you access like this like quad word. Then entire block 4 will be copied over to the cache, right? Because of temporal locality and spatial locality, if you access like a block 4, it's likely that you're going to access that like a specific word again in the future, and also those like a, words nearby. So you just copy the entire block of 4, even though you just requested like a specific word in it. Okay? Then here is the question. So now you already have like a certain like a blocks placed in your cache, right? Then the question is, new blocks is coming in. New block is coming in. Then there are two questions. First of all, where this block should go. So in this like a specific example, we have 4 different locations a block can go. Right? So first question is where this block should go, right? And second question is which block should be kicked out. Okay. So that's basically two questions. So let's say in this case, in this example, let's say this 4, actually goes to. This is like a block 4 actually should go to the first block in the cache. Then it actually kicks out the block 8. Right? So now block 8 will be kicked out. This like a block 4 will take its place. And let's say the next access is falling into the block 10. Now we access like a block 10 here. Then this one will be transferred into the cache. And let's say, this block 10 will be placed in the third block in the cache with some mechanism. Then now this one actually will be placed here, and you will kick out the block 14, which was there. Okay. So here is a general cache concept. Whatever. There's notion of a cache hit. Cache hit means, let's say you access it, you access memory, and the memory word you are accessing is currently in the cache. Then that is called cache hit. Okay. So let's say you want to access like a memory, something like a memory word in block 14. Then the data you're looking for is currently in the cache, right? So you can actually provide very fast access to the CPU. Let's say this is pipeline, because it actually comes from the pipeline here. So pipeline actually send the request to the cache. In this specific example, let's say if you want to access a word in block 14. This is called cache hit because the one we are looking for is currently in the cache, right? So let's say data in block B is needed. In this case, the B is like a 14. And if the block B is in the cache, then it's called cache hit. Okay, it's cache hit. But let's say if you request another like data, let's say now you request like a 12. Okay, so if you actually request like some data in block 12, then in this example, this block 12 is currently not in the cache, right? So this case is called cache miss. Okay, so one of the design goal in designing cache is how we can maximize cache hit rate, because we want to service as many requests as possible from the cache, because it's much faster storage, right? So in this case, what happens is, in this case, because this block B, block 12 is not here, so this will actually forward the request to the main memory. So now this block B is 12 here. So block 12 will be fetched from main memory and be copied over to the cache like this, right? And this cache B, block B will be stored in the cache, and kick out one of the existing one, possibly like kicking out one of the existing blocks in the cache. So there are two questions in this thing. As I said, we actually have to decide the two things. The first one is placement policy. So placement policy means it actually determines where this new block, like a 12, should go. Okay, so typically, once you actually have a certain block, generally speaking, cache actually limits the number of blocks that a cache block can go. In other words, let's say you actually have certain block ID, then that block ID, that block cannot go anywhere in the cache. It can only go to some subset of position in the cache. Okay, so that's called a placement policy. Whenever you fetch a new block from the memory, where this block should go. That's called a placement policy. And second one is replacement policy. So replacement policy is, let's say you have multiple choices. Let's say you have fetched a block, and then that block can go one of the n positions in the cache. Then the next question is, which one you should kick out, and which one of the 8 possible choices you should go, right? That's actually determined by replacement policy. So it determines which block gets evicted, which one should be kicked out of the cache. So in this specific example, let's say if your cache block can go anywhere in the cache, placement policy and replacement policy is almost the same thing, because you determine which one to kick out and which one to put in. It's the same. It's coupled in the same way, right? But if you actually if it's not true, let's say your cache block can go only one of the a subset. Let's say in the specific example, let's say if you, let's say your block 12 can go to one of these two things, one of these two blocks, for example, then this block 12 can go to either the first one or second block in the cache, right? Then actually you actually have to determine which one to kick out, right? Which one to replace. So by employing the replacement policy, you actually select one of the two. Maybe in this case, this one is selected. Then we replace like the original like one that are here, and now we place this new block in that location. So these two are important like design decisions for cache. Placement policy determines where this B can go. It's like some subset of blocks. This like a new block can go, and replacement policy actually determines which specific block will be kicked out among those like candidates. Okay. So you have to actually determine these two design issue. And generally, there are some like general caching concepts. We actually have like there are multiple causes of cache miss. So if you have a cache miss, there are multiple reasons why these cache miss can happen, and this is so-called like a 3C. 3 C's of cache miss. There are 3 reasons why we actually have a cache miss. The first one is like a cold miss. Second one is conflict miss, and third one is capacity miss. Okay. The cold miss is, of course, whenever you first access any block, there should be cache miss, right? Because cache is initially cache is empty, right? And whenever you actually have to place certain block into the cache, you actually have the cache miss first, right? In the first access to the block, you always have a cache miss. So this is called like a cold miss because cold miss occurs because the cache is empty, and the first access to any block actually causes cache miss. That's cold miss. That's the first C. And second one is conflict miss. So conflict miss is, as I said, most caches limits block at k+1 to a small subset of the block position at level k. In other words, let's say you actually had, in the previous example, you had block 12 from like a main memory. Then there are only like a small subset of positions this like a block 12 can go in the cache. That's like a typical design pattern. I mean, this is how we design cache. So, most cache limits, the position a block can go. So, conflict misses occur when the level k cache is large enough, but multiple data objects actually all maps the same block, same set of blocks. Okay, so maybe one of these the simplest like a placement policy. Let's say one of the simplest placement policies looks like this: block I and level k+1 must be placed in block I mod 4 at level k. Let's say this is kind of simplest, very simple like a placement policy. So let me give you an example why it works like this in the previous example. So let's say our placement policy so this one is a block 0. This is a block 1, block 2, and block 3. We have like 4 blocks, right, in the cache. And when we actually place a block, so this one is like a block ID. Let's say this is block ID. So our placement policy is that we want to actually place this one actually goes this block ID goes to block N. So if you have like a block ID, goes to block N, where N is block ID modulo 4, because we have 4 blocks. So let's say this is a very simple like a placement policy. So in this case, block 1 can only go to like a block 0, and block 1 can always go to block 1. Block 2 will always go to block 2, and block 3 will always go to block 3. What about block 4? Where this one should go in the cache? Block 0 again, right? So this one can only go to here, this one can only go to here, this one can only go to here. So in other words, all of these like blocks in the column 0 will go to block 0, and column 1 will go to block 1, and so on, right? The problem is, conflict miss looks like this. Let's say your memory access pattern was 0, 8, 0, 8, block ID 0, 8, 0, 8, 0, 8. Then what's going to happen? Yeah, so what will be the cache miss rate in this example? Cache miss rate, how many, in this access pattern? Cache miss rate. The percentage of cache misses for all the accesses. Let me do it this way. So first access, this one will cause cache hit or cache miss. This one will cache miss, right? This one will cold miss because it's the first access to the block, right? This one will be miss. What about second one? This one will cause cache hit or cache miss. No, this one is an access pattern. Your program's like your program's access pattern. Your program actually access this data, this data, this data, this data alternatively, right? Your program's like access sequence of access. Okay. So the first access goes to block 0. Second access goes to block 8. Third access go back to block 0. Fourth access go to block 8. This kind of synthetic like example, but it's not uncommon. Right? Sometimes it happens. So let's say first access goes to block 0, second access goes to block 8, third access goes to block 0, fourth access goes to block 8, and so on. You keep alternating. Then the first access will cause cache miss, right? Because it's miss. What about second access? This is cache hit or miss? Miss. Why? Oh, sorry. Initially, let's say cache is empty. Let's assume cache is currently empty. This is our cache. Don't worry about this part. Let's not worry about this thing. This one is not. Let's not worry about this. So let's say our cache is currently empty, and the first access actually caused cache miss, like a 0, right? And then this block 0 will be placed in the cache like this, right? What about second access? If you actually have a second access, it will cause cache hit or miss. Cache miss, right? Because another cold miss, because the first access to the cache, right? Cache block, right? So now, because of our placement policy, where should this one go? Block 0, right? Because our placement policy is, we divide block ID by modulo 4, and that will be your like a block ID in the cache, right? So this one will always go to here. So it will actually kick out, block 0, and the block 8 will take its place. And what about this third request? It will cause a cache hit or miss? Miss, right? Because block 0 is kicked out by block 8, right? So now block 0 is coming back. Like now this one is kicked out, block 8, and now the block 0 will take its place again. So it will cause a miss. And the next access will be either cache hit or miss. Again, miss, right? So this one will kick out, the cache 0, and this access itself will be cache miss again, right? So that's very bad situation, right? Because we have other like empty cache blocks in the cache, right? But they, block 0 and block 8, keep kicking out each other, and then generating cache misses, right? This is called conflict miss. Conflict miss is, it happens even though you still have some like empty space in your cache. It actually happens because the two blocks actually compete for the same cache block again and again, 2 or more blocks, right? So here, this is an example. Here, because the most cache actually limits the blocks a block can go. Those like blocks in the cache, a block can go, right? So in the previous example, we only limit to the like one specific position, right? So because of this like a limit, maybe multiple blocks actually map to the same like a subset, right? And then they actually conflict. They basically may compete for the same subset of the cache block, and then they kick out each other and then generate cache miss, even though there are some like empty space in the rest of the cache. Okay. In a sense, this one is happened by the inflexibility of caching, right? Because if you can flexibly cache this block to like different places, then that will actually help a lot. But in this specific example, it's very like pathological case. So conflict misses occur when level K cache is large enough. It actually has some like empty spaces, but multiple data objects all map the same block in the level K, right? So referencing block 080808 would miss every time. That's conflict miss. Finally, the capacity miss. The capacity miss occurs when the set of object active like cache blocks, which is called a working set, by the way. Working set is greater than the cache. Sometimes, let's say our access pattern is something like this. Let's say, our access pattern is something like 0, 1, 2, like a block, block 0, block 1, block 2, block 3, block 4, block 5, block 6, block 8. You keep repeating this pattern. 0, 1, 2, 3, 4, 5, 6, 8. Not 8, sorry. 7. 0, 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3, 4, 5, 6, 7. Then this is working set, right? This is your working set, like a accessing like a set of memory location you're accessing. But that like it doesn't fit in your memory. That doesn't fit in your cache, right? So because this is called capacity miss, because the set of active cache blocks, like those you are accessing, is larger than the cache, right? In this case, this is 2x larger than the cache. So you can already fit like the entire data set into the cache, so that actually causes capacity miss. So here is like an example of a caching and memory hierarchy. Not worry about this like this cache, browser cache, all this thing. Let's worry about only like this, like a red like rows. So registers generally what is cached? It's like a 4 to 8 byte words, because if you have like RAX register, it actually holds like 8 byte value, right? 8 byte word, the quad word. So this one is generally hold like 4 to 8 words, and whereas cache is a CPU core within the pipeline, and latency is like 0. 0 means that if you place like the address, it comes out immediately, right? So it's like a sequential logic, right? Combinational logic, right? So and it's managed by compiler by register location. So that's the register, the top level of the hierarchy. And level 1 cache, typically it's like 64 byte cached in 64 byte blocks, and it's on chip level 1. And latency is like can take as many as 4 cycles, but it's kind of very conservative. Sometimes it takes like only 1 or 2 cycles. That's also fine. That's also pretty common. Somewhere between 1 and 4, I would say. Somewhere between 1 and 4 cycles. And level 2 cache also, it actually cache in the unit of like a 64 byte blocks. So this one is on chip L2, level 2, and latency is somewhere like 10 CPU cycles. That's kind of typical value. And the virtual memory, so the main memory is used as cache for disk, and as he said, it's actually cached in the granularity of 4 kilobyte pages. Okay, so we actually cache those like block. Basically, entire disk space is divided as partitioned as like a 4 kilobyte blocks, and then whenever you have like a cache miss, which is called like a page fault, by the way, whenever you have a page fault, 4 kilobyte like a block will be copied over to main memory, the page granularity. So that's basically the virtual memory is managed by hardware and software, hardware and operating system, and buffer cache, disk cache, and network buffer cache, all these things also like different layers of cache, which is out of scope in this course. Okay, so that's it. So we just introduced concept of memory hierarchy, and also what's the locality. We actually talk about the two types of locality, spatial locality and temporal locality, and we make use of exploit these properties to design hierarchical memory system. And different hierarchy actually has different trade-offs, right? Upper level devices actually have smaller capacity but faster, but in the lower level memory level, they actually have like a greater capacity and cheaper, but actually much slower. And by organizing this memory system in hierarchical manner, the goal is service this memory request as many as possible in this like upper level, and still this lower level actually provide high capacity for your system. Okay, so memory hierarchies based on caching close the gap by exploring locality. That's the goal of designing cache memory. So we're gonna next time we're gonna continue how we can actually design the cache. So as I said last time, as we did for the pipeline, we're gonna go over like three design issues. The first one is how what is cache, and secondly how cache works, and third how we can make well-performing how we can achieve good performance with caches, right? So we're gonna go over all these three topics in the next lectures, and we're gonna also talk about this like a virtual memory system, because it's like a caching between disk and main memory. Okay, that's called like virtual memory. So we're gonna also go over this virtual memory system in this course. So next time, so we're gonna basically how we can design these blocks: data memory and instruction memory in fetch stage in the fetch stage of the pipeline, and in data stage in memory stage in the pipeline. We actually have two like memory blocks, right? So we're gonna actually these are like caches. So we're gonna basically discuss how we can design these two memory blocks in greater detail. In the previous pipeline design, we simply assume it only takes like one cycle to access, right? But that's not true. Sometimes if you of course if you have a cache hit, then maybe it only takes one cycle. But if you have a cache miss, then actually you have to stall the pipeline and go to the main memory and fetch the block into the cache, and then you restart the instruction, right? So generally speaking, this one actually, if you there's cache hit, it only takes one cycle, but if you have cache miss, it takes 100 cycles, for example. So we're gonna make these blocks realistic. Although so far we have assumed it only takes like one cycle, but that's not really true, like real like memory. So we're gonna basically make these blocks real, more realistic in the next course, in the next like lectures. Okay, so I think that's pretty much it for today. Is there any questions or? All right. Thank you for showing up again. I'm gonna see you guys on Tuesday. Also, we're gonna have like makeup class on Tuesday evening. So please, if you can, please show up. Otherwise, please watch the video yourself. All right. Thank you.